something just shattered our understanding of the solar system. Astronomers have confirmed that 3IRI/ATLAS, the third interstellar visitor ever detected, is exhibiting an orbital shift that defies standard explanations rooted in gravity or even the most powerful gas jets from cometary outgassing. This colossal cosmic intruder, measuring up to 5.6 kilometers in diameter, is hurtling through our neighborhood at an astonishing 61 kilometers per hour second, fast enough to break free from the sun's gravitational grip and vanish back into the interstellar void. But here's the twist that has experts scrambling. Sunlight pressure, volatile gas eruptions, and all the usual forces we've relied on for decades simply don't account for its subtle but persistent deviation. If outgassing alone can't explain why 3I/ATLAS is bending the rules of celestial mechanics, what hidden influence is steering this behemoth? The implications for astronomy and for safeguarding our planet from unexpected cosmic threats couldn't be more profound. So buckle up as we dive deep into this enigma, because what we're witnessing might force us to rewrite the playbook on how objects move through space. Stick around to the end, where we'll explore the wild theories and what's coming next. You won't want to miss how this could change everything we know about our place in the galaxy. Imagine the thrill of discovery on July 1st, 2025, when astronomers at the NASA-funded Asteroid Terrestrial Impact Last Alert System, ATLAS survey in Rio Hurtado, Chile, first spotted an anomaly streaking across the night sky. This wasn't just another asteroid or comet from our own Oort cloud. It was something that shouldn't be here, an object barreling in at 61 kilometers per second, more than twice the speed of previous interstellar visitors like 1I/ʻOumuamua and 2I/Borisov. That's equivalent to 221,000 kilometers per hour, a velocity so extreme it guarantees this wanderer will slingshot around the sun and escape forever, unbound by our star's pull. Within hours, global observatories mobilized, from the Hubble Space Telescope to the James Webb Space Telescope, JWST, confirming what many suspected. This was 3I/ATLAS, the largest interstellar object humanity has ever tracked, with a nucleus estimated between 0.32 and 5.6 kilometers across, potentially up to 3.5 miles wide. For context, that's larger than the previous record holder, 2I/Borisov, and dwarfs 1I/ʻOumuamua's mere 400 meters. Halley's Comet, a solar system icon, spans about 15 kilometers, but 3I/ATLAS's sheer bulk makes it a heavyweight champion among cosmic nomads. Its orbit, a hyperbolic eccentricity of 6.1396, the highest ever recorded for an interstellar object, tracing a near straight line through our system with an inclination of 175 degrees, practically retrograde and hugging the ecliptic plane. This trajectory screams outsider, originating from some distant star system billions of years ago, now paying us a fleeting visit before vanishing into the abyss. As data flooded in from telescopes worldwide, one detail electrified the astronomical community. 3I/ATLAS wasn't following the predicted path. Not dramatically, not in a Hollywood-style swerve, but with a subtle veer that's impossible to ignore when plotted against high-precision models. Orbital experts, armed with centuries of Newtonian physics, factored in every variable: solar gravity, planetary tugs from Venus, Mars, and Jupiter, even the faint pressure of sunlight on its surface. Yet the residuals persisted. Tiny discrepancies between where 3I/ATLAS should be and where it actually appeared in the sky, stacking up systematically across hundreds of observations. This isn't random noise from faulty instruments. It's a consistent offset reported from sites like Mauna Kea to La Silla, spanning an observation arc of over 100 days. For astronomers, this is more than a glitch. It's a crisis of confidence in our fundamental understanding of celestial motion. If a visitor this massive can nudge itself off course without a clear cause, what does that say about the invisible forces lurking in our cosmic backyard? Hang in there, because as we unpack the science, you'll see why this could be the tip of an interstellar iceberg. Comets aren't passive travelers. They're dynamic beasts shaped by an eternal battle between gravity's inexorable pull and the chaotic whims of outgassing. Think of a comet as a frozen cocktail of ices, dust, and rocks, a dirty snowball that awakens as it nears the sun. Solar heat penetrates the surface, sublimating ices into gas, which erupts in jets that act like natural rocket thrusters. These outbursts can propel the comet in unexpected directions, much like an untied balloon zigzagging across a room. We've seen this up close. The European Space Agency's Rosetta mission to Comet 67P/Churyumov-Gerasimenko in 2014 to 2016 revealed how just 10% of the surface drove most activity, with plumes not only altering the orbit, but even tweaking the nucleus's rotation rate. Models incorporate these non-gravitational forces, quantifying gas release in kilograms per second and calculating the resulting momentum. For typical comets, water vapor dominates, ejecting at hundreds of meters per second and shifting paths by thousands of kilometers over time. The rules seem straightforward. More gas equals more push, but it scales with mass. A lightweight comet budges easily, a dense giant resists. Decades of data from icons like Halley and Hale-Bopp validate this. Know the jets and mass, predict the motion, but 3I/ATLAS, it's testing these limits like never before. Its hyperactivity starts far out, at 6.4 astronomical units from the sun, where water ice shouldn't sublimate, hinting at volatiles like carbon dioxide or carbon monoxide driving early outbursts. As it closes in, the coma, a glowing envelope of gas and dust, reveals its secrets through spectroscopy. Enter the chemical enigma. JWST data from August 6, 2025, shows a coma dominated by carbon dioxide with an 8-to-1 ratio to water, unheard of in solar system comets, where water usually reigns supreme. Production rates: CO2 at 129 kilograms per second, water at 6.6 kilograms per second, carbon monoxide at 14 kilograms per second, and carbonyl sulfide at 0.43 kilograms per second. That's a torrent of gas, enough to form a visible tail and plume, even glowing green during a recent lunar eclipse due to cyanide emissions. But here's the kicker. Even this outpouring falls short of explaining the orbital deviation. For a nucleus potentially billions of tons heavy, the momentum from these jets, calculated via thrust equations, barely registers against its inertia. Dust loss, estimated at 6 to 60 kilograms per second from Hubble, adds little more. The Very Large Telescope spotted 22 emission lines of atomic nickel at 4.7 times 10 to the 22nd atoms per second, sans iron. A bizarre decoupling not seen in typical cosmic materials. This suggests exotic organometallic compounds or nanograins breaking down. But again, it doesn't bridge the force gap. Orbital prediction should be routine. Input mass, velocity, gravitational influences, and out pops a trajectory. For 3I/ATLAS, the hyperbolic path sketches a clean arc. Perihelion at 1.36 astronomical units on October 29, 2025. Closest to Earth at 1.8 astronomical units, 270 million kilometers on December 19. But overlay real observations, over 600 data points from May 7th onward, and the cracks appear. Residuals drift systematically, defying adjustments for outgassing or radiation pressure. This non-gravitational acceleration echoes the past, but on a grander scale. Keep watching, because we're about to connect the dots to an infamous predecessor that still haunts the field. 6 years earlier, in 2017, 1I/ʻOumuamua stunned the world, a cigar-shaped shard, 400 meters long, tumbling through at 26 kilometers per second with no visible coma, yet accelerating anomalously at about 5 times 10 to the power of minus 6 meters per second squared. No jets, no dust, just a persistent push-defying gravity. Theories range from hydrogen outgassing to solar sails, with Harvard's Avi Loeb famously proposing artificial origins in his 2018 paper. Now 3I/ATLAS revives that déjà vu. Larger by orders of magnitude, its deviation requires far more force, yet observations show similar residuals. systematic offsets hinting at an extra acceleration of comparable magnitude. Unlike Oumuamua's dryness, 3I/ATLAS is overtly cometary, with a fan-shaped dust plume and anti-solar tail. But the math still doesn't add up. The outgassing horsepower is insufficient for its estimated mass. This scale amplifies the puzzle. 3I/ATLAS's bulk, potentially thousands of times Oumuamua's mass, demands a push akin to industrial thrusters. Standard Comet physics says more mass means less responsiveness to jets. Yet here it drifts. Fragmentation, no major breakups detected. Low-density rubble pile, the chemistry suggests solidity. Then come the outliers. Loeb's July 16, 2025, paper posits exotic possibilities, like an ultra-thin solar sail or engineered structure maximizing radiation pressure. Mainstream voices, including NASA, debunk alien claims, attributing anomalies to unmodeled outgassing or measurement errors. Yet as it changes color and reveals green glows, debates rage on Reddit and in journals. Is this natural weirdness or something more? The statistical oddities, high eccentricity, retrograde path, chemical quirks, warrant discussion, but consensus leans natural. Why does this matter? These aren't mere rocks, they're emissaries from alien stars, carrying primordial chemistry from distant births. 3I/ATLAS's CO₂ dominance and nickel anomaly hint at formation in a carbon-rich environment, perhaps around a red dwarf. As the Vera C. Rubin Observatory's legacy survey of space and time ramps up, expect dozens of interstellar detections annually. If models falter on 3I/ATLAS, imagine the flood of mysteries ahead. Future probes like ESA's Mars Express and ExoMars Trace Gas Orbiter will scrutinize it near Mars on October 3, 2025, while JUICE and Europa Clipper join in November. This could unveil new physics or just refine our tools. On July 1, 2025, the Atlas survey unveiled 3I/Atlas, an interstellar comet racing at 61 kilometers per second with a 0.32 to 5.6 kilometers nucleus. Tracked by NASA, ESA, and global teams, its orbit shows unexplained shifts despite CO₂, heavy outgassing, 8-to-1-to-water, and nickel emissions without iron. Echoing Oumuamua's 2017 anomaly, no full explanation exists, though NASA dismisses exotic theories. With perihelion looming on October 29th, data pours in, but the rulebook remains incomplete. As surveys gear up for more visitors, subscribe to join the chase. What do you think powers 3I/ATLAS's defiance? Now let's expand deeper to truly immerse you in this cosmic drama. The discovery of 3I/ATLAS didn't happen in isolation. It builds on a legacy of skywatching that's evolved dramatically. The Atlas system, operational since 2015, scans the heavens for near-Earth threats. But snagging an interstellar gem like this underscores its versatility. Pre-discovery images from May 7, 2025, via NASA's Transiting Exoplanet Survey Satellite, TESS, showed early activity at 6.4 astronomical units, far beyond where water activates, pointing to hypervolatiles like CO₂ kicking off the show. This pre-covery extended the arc, refining the orbit from initial estimates. Diving into the orbital mechanics, the eccentricity of 6.14 means its path is more arrow than ellipse, with a hyperbolic excess velocity of 58 kilometers per second, confirming extrasolar origins. It grazed Mars at 0.19 astronomical units on October 3rd, Venus at 0.65 astronomical units on November 3rd, and will skim Jupiter at 0.36 astronomical units in March 2026. No close Earth flyby, keeping it safe at 1.8 astronomical units. But the anomaly? Preliminary reports from July 2025 noted photometric and astrometric oddities, with residuals suggesting a non-gravitational parameter, A2 radial acceleration that's elevated beyond gas models. Loeb's analysis highlights how the size, if at the upper end, amplifies the force needed, potentially requiring novel explanations like asymmetric heating or unseen volatiles. The Comet's polarization, highly negative at small phase angles, mirrors trans-Neptunian objects, suggesting pristine, unprocessed material. Dust shows reddish hues, depleted in carbon chains, while heavy metals like nickel vaporize preferentially. Cyanide production ramped to 17.6 grams per second by August, painting a picture of a chemically alien world. As it neared, a sun-facing plume emerged, not typical but explainable, yet cumulative effects strained the budget. Comparing to 2I/Borisov, discovered in 2019, that comet was water-rich and fragmented, its anomaly minimal. 3I/ATLAS, with its CO₂ dominance, might represent a different breed, perhaps from a system with volatile-rich planetesimals. The green glow from diatomic carbon or cyanide during the September 15, 2025, lunar eclipse added visual flair, captivating amateur astronomers. Theories abound. Mainstream favors enhanced outgassing models, perhaps hydrogen or exotic ices. Loeb and contrarians invoke artifacts, citing probabilities, retrograde, planar orbit, size rarity, as too coincidental. NASA counters, it's a comet, period, with anomalies resolvable via better data. Changing colors? Likely dust composition shifts under heating. Looking ahead as 3I/ATLAS fades post-perihelion, reaching magnitude 13.8 in September 2025 and dimming further, ground-based views require telescopes. But with Rubin online, the era of routine interstellar detections dawns, promising answers, or more questions. This story isn't over. It's evolving daily. From discovery to debate, 3I/ATLAS challenges us to question the cosmos. What invisible force tugs at it? Natural quirk or cosmic clue? Subscribe, like, and comment your theory. Together, we'll watch as science unravels the mystery.